Just a quick disclaimer that everything covered in this presentation is my personal views and opinions, and it doesn't reflect the Army Corps of Engineers or the U.S. Army. Just got to toss that out there. Just a quick outline. Another disclaimer that there's a lot of math in this, so let that be a trigger warning if that upsets anybody. It's super abstract, so it's kind of necessary to run through the formalism. Then I'll be talking about identifying barometric frequencies. Again, it's also rather abstract. Then discussing how it relates to source configurations and sensitivity to particular frequencies. Then a case study of the Niagara Falls storage site, and then just an open discussion at the end. Just a little bit about myself. I'm a health physicist with the Army Corps of Engineers out of Buffalo, New York. We predominantly work on environmental remediation for sites impacted from the early Manhattan project, so a lot of radium contamination at our sites. The Niagara Falls storage site is fairly unique. It's sort of a uranium mill tailings-like facility, and I'll get into some more details later, but it's an interesting case study that applies across the board. So if you've ever done any sort of study or research on broad soil gas transport, you've probably seen this equation at the top here. It's a differential equation describing the concentration change over time with regards to fairly robust characteristics of processes. It's essentially saying that the concentration is expected to vary based on diffusion, which is the first terms, advection, and then any radiological decay and ingrowth from potentially intrinsic radium in your medium. This gets very complicated if you try to solve these straightforward because a lot of it's super nonlinear and very complicated. So instead we're going to pull out this advection term, kind of explore that deeply, and then see what we can get out of that. Just a quick definition, advection is the transfer of heat or matter by the flow of a fluid, and making some roughly true-ish assumptions, we can kind of make some generalizations with respect to temperature and relate that over to pressure. This term K here, it's going to show up a lot. It's the permeability of the medium, and it's typically given in units of meters squared. This new term is going to show up again. It's the dynamic viscosity of the fluid, and this can vary between radon and other types of soil gases. And then P is just broadly the pore space gas pressure. So if we think of this source term as a vertical column of some porous material with length L, and we consider some fixed pressure at the bottom of this column, and then pressure variations on the surface, essentially the variations in atmospheric pressure. The question we really want to answer is how does this pressure manifest itself throughout the structure, essentially through the pore space of the material. This has been studied extensively in terms of temperature itself, but like I mentioned, we can make some ideal gas law assumptions. So assume it's roughly constant porosity. Assume over the time scale that we're considering that it's roughly isothermal, so temperature change is fairly negligible. Then just assume that this NR term, they're essentially constant. Just assume it's constant in this situation. So the linear heat flow of any particular fluid is broadly given in terms of the spatial gradient and the temperature gradient, or the time gradient. With these assumptions, we get this second term here. So we see that the change in pressure over time is scaled by the second order differential of the pressure with respect to the space. And this interesting term dP, this dP term is called the pneumatic diffusivity. If you're familiar with physical diffusion, this is essentially the same concept for describing how a pressure field is going to diffuse through a porous material. It's directly proportional to the permeability of the pore space, as well as the mean absolute pressure, the dynamic viscosity, and the gas phase porosity. This is complicated, so luckily we can cross a lot of it out. There are general solutions to this second equation here, assuming that the pressure responds somewhat sinusoidally. So if there's a sinusoidal variation on the surface, then with depth over time, the pressure is expected to follow this long equation here. Luckily, it's essentially two parts. There's a steady solution, a transient solution. Transient meaning that as the time extends to infinity, this contribution, decays to zero. So we can essentially cross it out because we're not interested in the initial conditions. We just want to know how this responds over a longer period of time. The important takeaways out of this are the scaling term A, and more specifically within that, it's this theta term called the pneumatic attenuation length. If there are any health physicists in the room, they might be familiar with the relaxation length for any particular material flowing through a medium, or essentially if you're doing any sort of shielding analysis with gamma rays, it's essentially the distance that you would expect for a particle or a ray to travel before it's either decayed or it's effectively shielded. In this instance, you can think of the pneumatic attenuation length as the distance, or more specifically the depth, that a pressure field would be expected to percolate into a porous material before the phase shifts in the pressure signal. And that's why you see this omega over 2 term, because if you think of a wavelength of a sine, half of it's positive, half of it's negative, and we're interested in either the positive or the negative half. All right, so this sounds super abstract. Why would anybody care about any of this? The flow of a fluid is proportional to the gradient of a pressure field, not necessarily the absolute pressure. So the question is, where is the spatial gradient not negligible? Or more specifically, how deep does this non-negligible pressure gradient extend into any particular situation? We're going to be looking at essentially discrete or heterogeneous subsurface sources. So say you have a pocket of either radon or any sort of subsurface soil gas you're considering, a pocket of rich soil gas at a fixed depth with an essential clean cover, and just ask yourselves the question, for a particular frequency, does this pressure gradient extend deep enough to where it reaches this rich soil gas? It's a super abstract topic, so I do apologize, but I'll try to make it a little more straightforward with some examples later. I mentioned earlier that this pneumatic attenuation length is directly related to the frequency of a pressure signal. So for higher frequencies or a lower period, like your diurnal cycles or all of its various harmonics, you can see that this pressure tends to drop off fairly quickly in terms of depth. Coinciding with that is a steeper gradient in fairly shallow depths, which you'd expect and we see very frequently with daily radon cycle that tends to be higher in the morning, tends to drop off as the day goes on as the pressure changes. But you can see for these longer periods, I gave an example of 24 days here. So these are really low frequencies, like 10 to the minus 7 hertz, and it's extending over days to weeks if you have any trending pressure cycles in your local climate. You can see that the depth of this pressure field actually extends fairly deep. Just as an example here, you can see a 1 day, for this particular example that I give, the depth of this 1 day cycle tends to drop off before 1 meter in depth, but if the frequency extends, over several days or several weeks, this can extend several meters down, which can start to get interesting in some of these situations. The next topic is a Fourier series and a Fourier transform. So this is kind of signal processing. So oftentimes when you look at a time series of pressure, it's super noisy. It just looks like random numbers all over the place. But something that you can seriously consider are there any legitimate underlying frequencies that might be of interest to me or to anybody exploring some of these sites. So essentially a Fourier series is a series expansion of a time series represented as a summation of sines and cosines. So I give an example here of some noisy time series in the middle, and it's literally the summation of 4 different sinusoids. So there's a 24-hour component, a 12-hour component, an 8-hour component, a 6-hour component. And this is your diurnal and the first 3 harmonics of a pressure, an assumed pressure time series. The corresponding transform that you can make is a Fourier transform. So that's where you take this time series and you decompose it into a function of frequencies, or you can take the inverse as a function of periodicity. So for these 4 specific frequencies, you see a noisy time series. A Fourier transform is essentially going to show you this figure on the right, where you'll see discrete peaks for discrete underlying frequencies. So I have 24 hours, 12, 8, and 6 hours, and I'll see peaks at 24, 12, 8, and 6. So what does this look like in reality? So on the top, I have actual hourly measurements from the Niagara Falls International Airport in upstate New York. And light blue are the actual hourly measurements, and this thick purple line is a running average over 10 days. So if you were to look, just directly at the hourly measurements, it's a bunch of nothing because it's super noisy and nobody cares about anything. But if you look at this in terms of running averages, you can see that there are fairly discrete, cycles that extend over longer periods of time that might be of interest to people. On the bottom is a Fourier transform of the same pressure signal on the top. And you see that there actually is a peak coinciding with 30 to 33 days. I'm not a meteorologist, don't ask me what it is, ask your weathermen friends if you have them. But it kind of, reinforces this concept that there could be underlying frequencies that happen over extended periods of time. The interesting takeaway with this is that the solution I mentioned here is for one single frequency, but if you can represent your surface fluctuations as a Fourier series, like I mentioned earlier, the steady solution to the system actually also follows essentially a Fourier series. So if you can identify, legitimate, discrete, underlying pressure frequencies in your pressure time series, then the solution would also be expected to follow across the same frequencies. So the punchline of this is that if you can identify some cycle that occurs with some period, you may be able to expect radon fluctuations to occur over the same cycle. And it's incredibly site-specific and varies based on your geographical location. Here I just have a couple examples of what this might look like in different parts of the countries, and is this something crazy to even think about? It's kind of laid out geographically consistent. So on the top left there, I just have an example from Spokane, Washington. This was also reproducible in other cities in the area like Seattle, Portland, Oregon. There tends to be a 14-day signal that typically, a 14-day period of a signal that tends to manifest itself consistently. And again, these are taken over a decade-long interval. So over a 10-year span, there tends to be an underlying cycle approximately 14 days in the Pacific Northwest. As you work your way eastward towards the Great Lakes, as shown in Chicago here, and also showed in Niagara Falls, there tends to be a 30 to 33-ish cycle. In between in Albuquerque, you see influences both. And as you work your way into the New England region, as shown in Boston, you tend to see this 21 to 24-day cycle. And again, it's consistent regionally over a decades-long span. As you work your way south, you kind of don't really see anything. They're more heavily influenced by just random weather fluctuations or storm or whatever systems are roll through. Again, I'm not a meteorologist, but I'm smart enough to know that there are things that you can see in a series decomposition. Right. So the question you might ask yourself is, I can see these peaks in a Fourier transform. How do I know if it's actually related to a radon cycle? The obvious answer would be, well, perhaps I can take, hourly measurements, of the pressure and of the radon itself, whether you're interested in an indoor air concentration or a surface flux that I'm more so interested in. The same idea essentially applies. But like I mentioned earlier, this is an ultra low frequency that you're concerned with. I mentioned it's roughly 10 to the minus 8th hertz or 10 to the minus 7 hertz. And if you want resolution in your Fourier transform, it's inversely proportional to the size of the data set. So if you're looking at 10 to the minus 8th hertz, you're probably looking at 10 to the 8th seconds, which is several years to a decade of continuous unbroken measurements that are consistent of what you're actually looking at. I challenge you to find one because I don't think anyone has something like this, especially if it's indoor. This means no HVAC systems, no nothing, consistent hourly measurements over essentially a decade. If you did have one, that'd be awesome, because then you can overlay these two decompositions and see if the peaks line up. As an example here, just over, days, you can see that there's a very obvious overlap. At one day, this is, a diurnal fluctuation that everyone would expect to see, but the question is what happens as you extend into these longer and longer cycles? An alternative option is to try to model something like this. So there's actually an open source code called the RN Mod 3D code from Klaus Andersen in Denmark. It's a finite model, numerical model of soil gas and radon transport. So it essentially models the diffusion of radon individually and then the bulk flow of just generic soil gas, combines the influence of both of them to give you, an overall dynamics of your soil gas. It's capable of three-dimensional flow, transient Darcy flow, so your bulk soil gas, and variable diffusivity and permeability in space and time. So you can make discrete layers, You can make discrete layers with their own individual diffusivities and permeabilities. The limitations are essentially the same assumptions we made, so roughly isothermal and constant porosity. So I identified 6 sensitivity case studies that you have here. So first two are a homogeneous source, where you essentially have one thick layer of a material with intrinsic radium, such that you'll have, just a generic pore space radon concentration throughout the material.
About 3 minutes.
Cool.
3 minutes.
Great. And the second have, the heterogeneous source that we're more interested in, so a clean cover and a radon-rich material underneath that. And essentially what I'm going to do is test this over different permeabilities, essentially different pneumatic attenuation lengths, and for a high frequency of 1 day and a low frequency, or a high frequency of 24 day and a low frequency of 1 day. If you're interested in this, you can, take the time to look at it later, but the main takeaway I have circled in red here are, you can see for, let's take case 5 as an example. So you have an instance where for a 1 day cycle, your pneumatic attenuation length is less than your cover thickness. And essentially your pressure gradient is never extending itself deep enough into the rich soil gas. So you wouldn't really expect much, enhancement of soil gas emissions. However, as your frequency grows, this non-negligible pressure gradient extends deeper and deeper, 4.5 meters in this instance, and you start to see noticeable enhancements of your either your surface flux or your soil gas emissions. As your permeability grows, you see this effect magnified here. I'll skip that for sake of time. Essentially, what are some conclusions we can draw for this, and then literally where does it come from in the formalism? The first is that the surface emission or the surface flux tends to increase across frequencies as the permeability increases. Of course, if you have a higher permeability, you're going to see more gas flow in any particular direction. The second term is for a homogeneous source. You'll see that for increasing barometric frequencies that you would expect to have a higher gas flow. Third term is really the one that I kind of wanted to talk about here and essentially identify, is if you have a discrete or a heterogeneous subsurface source configuration, if your periodicity of an underlying pressure signal tends to grow, so you get lower and lower frequencies, if this pneumatic attenuation length is greater than your cover thickness, you can start to see some influence to where you're pulling soil gases from deeper and deeper into the structure. So I mentioned the Niagara Falls storage site. It's essentially a landfill with about 2,000 curies of radium in it, so it's pretty hardcore if anyone cares about radium sources. It's pretty cool. Takeaway is that there's approximately 1 to 1.5 meters of clean cover and then an insane amount of radium and very rich soil gas underneath that. So as a health physicist, I'm tasked with monitoring radon flux or surface emissions out of this landfill. I started to notice, very hardcore fluctuations in radon flux over about 4 or 5 orders of magnitude over a span of about a couple days, couple weeks. Kind of just identifying here that, again, I have the actual pressures. You can see the long-term cycles in dark blue. It's the emanation of gas from deeper in the structure tends to coincide with these longer-term troughs in your pressure system that essentially you wouldn't really see if it was a homogeneous source or if it was a higher frequency. Just some broad conclusions. This isn't specific to radon. In fact, it's probably more applicable to vapor intrusion because you do see these deeper sources. The rule of thumb for a lot of people is that advection is negligible, but that's actually not always the case if you have these compatible configurations where you have a frequency and a permeability which creates these pneumatic attenuation lengths that are significant relative to your cover thickness. A lot of these conditions can be highly seasonable, specifically the saturation in your material. And then the takeaway with this is if you can predict these pressure cycles and it's compatible with your geological configuration, you may be able to predict these sort of intermediate term radon cycles and essentially keep that in mind if you have a structure similar to this or a situation that may be similar to this. So you may know, if you're looking for an actual minimum, consider a short-term test coinciding with a pressure trough. If you're more so interested in a mean over time, perhaps consider a longer test, or, offset them with different points of a pressure system. So that was a lot. It was kind of a shotgun approach. Here's my contact information, a beautiful picture of Niagara Falls if anyone's interested in. If anyone has any questions, I'd be happy to answer it here, offline, whenever. It's kind of general points. Thanks.